Okay, so in this video, we're going to look at some examples of how to actually work with the mole as a unit of conversion or a bridge between number of particles and the number of grams of mass in something. So again, remember, keep this diagram in mind, or this relationship that we have. We're always going to work through moles to convert. So first step in a problem like this is to understand what's given to you. Figure out whether you're here, whether your given information is on this side of the bridge, you're given atoms or number of particles or number of objects or something, or whether you're here already. Okay, you might be given a number of moles, and in that case, you're standing on the bridge already, or whether you're given grams. And then whatever the question is asking you will determine which direction you want to move across the bridge and which conversion factors you're going to want. So if I'm starting with grams, I'm given grams of something, and I'm asked for a number of particles in the object, then I'm going to need to do two conversions, go onto the bridge through moles and then across. If I'm just asked to find the number of moles, then it's only one conversion from here, and so on. Okay, you'll see how this works as we look at each problem. All of these problems can be found in the chapter review for chapter 7 on pages 196 and 197 in your textbook. So if you wanted to look at these, this is where I pulled these from. They're similar to some of the homework type problems that I will be giving you shortly. So first question, number 12a from the chapter review. How many moles are in 37.0 grams of Fe, which is iron? So the given information for us is 37 grams of iron. All right, so just like any unit conversion, that's what we're going to want to start with. So we write that out. And then we ask ourselves, what am I converting to? Okay, which direction am I going on this bridge? In this case, we're asked to find a number of moles based on this. So if I look at my bridge, I'm given grams, so I'm standing here at present, but I want to be here. Okay, I want to go this direction across the bridge. So I need a conversion factor that relates number of moles for iron to the number of grams per iron, okay? And this is what we call the gram formula mass, or since iron is an atom in this case, it's the gram atomic mass or the molar mass. These all mean the same thing here. So for iron, if you look at your periodic table and you find the atomic mass for iron, it's 55.85 AMUs. Which means that the conversion factor I will need here is 55.85 grams of iron per mole. And I want to orient this in a way that is going to cancel out the units that I don't want and keep the units that I'm trying to end with, which is the number of moles. So in this case, I want this version of the conversion factor. So 1 mole of iron is equivalent to 55.85 grams of iron. And now I've canceled the units that I am starting with, and I am ending with units that I want to get to. So everything is set up correctly here. And if I do the calculation, you'll find that it comes out to be 0.662 moles of iron. Okay. There is an abbreviation for moles. You might see it MOL like this. It's not much of an abbreviation though, obviously, so I usually don't use it. I just write out moles in most cases. Sometimes you also see chemists will write just mole. Even when it's plural, they'll put mole. Okay, so this is our number, but again, in chemistry, we want to typically, most of the time we want to be in scientific notation, so I'll ask you to put these answers in scientific notation. So if we convert this, it's going to be 6.62 times 10 to the negative first moles of iron. Okay, now it might seem a little bit tedious to keep the whole unit in the sense of including the type of atom or compound that we're working with, but when we get to the next chapter and we start doing stoichiometry problems, you'll see that this is actually useful. You will want to keep track of what element or what compound you're working with in each part of your conversion factor. It will, in fact, be relevant and could lead you to problems if you don't use it. So final answer, 37.0 grams of iron is equivalent to 6.62 times 10 to the negative first moles of iron. Okay, so it's a little bit more than half of a mole of iron. The other thing I wanted to point out about working these problems in general, the other thing was to keep track of your significant figures. Okay, these significant digits do apply in these problems. Now, this is not necessarily a measurement that they're giving us here. We don't really know that this was a measurement. It's not explicitly told, but in most cases in real chemistry, you're going to be working with measured quantities. And so we're going to treat this as if it's a measurement, which means that from this number, we have 3 significant digits. And the conversion factors are really definitions. So significant digits do not apply to definitions, right? They're not applicable. So you'll have a mixture in these conversion problems of numbers that are measurements and numbers that are just conversion factors. And so significant digits will apply to some of those, but not others. But since there are measurements in the problem as a whole, the final answer does need to follow the rules of significant digits, and significant digits do apply to the whole situation taken in its entirety. So we have one number with 3 significant digits here. Again, these unit conversions are all just multiplication and division, so we find the number with the fewest significant digits and we keep that number of significant digits in the answer. So here there are 3 from this number. This would be 4, but it's a definition. It's more or less, okay, or it's close to being an exact, like, counted quantity in a sense. So we don't apply significant digits to this. So we only have one number with 3 significant digits, which means we keep 3 significant digits in the answer as well. And again, this is another reason for going to scientific notation, is to be clear about how many significant figures we have. So keep that in mind in all of these. At the end of a problem, I will normally, again, state how many significant figures we should have. Okay, let's look at another example. So the last problem was an example of converting from grams to moles. In this case, we are given a number of moles of some compound. Okay, in this case, it's dinitrogen tetroxide. Just to give us a little bit of practice with our naming. Tetroxide, should leave that A out probably. So again, we are given information, we write it down to start. 0.0387 moles of N2O4. And in this case, we're going to mass. So this is actually the opposite direction of the last problem. We're starting here on the bridge. We have a number of moles, and we're asked to find a mass, okay, which will be most likely in grams. So we're going now this way. So I need, again, a conversion factor for molar mass. I need a relationship between moles and mass for this compound. Now I won't go through this in detail because we did this in the last video for examples like this. But if I add up all of the atomic weights of the elements in this compound, I'm going to get 92.02, okay? If I add up all the AMUs for the 2 nitrogens and the 4 oxygens all together, the total is 92.02 AMUs, which means that the molar mass is 92.02 grams per mole. Okay, and again, I could write that either way here. In this case, though, I'm starting with moles, so I want the one that has moles on the bottom so that they will cancel, and I'll be left with what I'm looking for, which in this case is mass. So I want this version of the conversion factor. Okay, these units will cancel. And when I perform this multiplication, again, I have 3 significant digits in this number. Okay, remember the zeros before or to the left of the terminating numbers in the decimal are not significant. So I have, again, 3 significant digits here, and this is the conversion factor, so significant digits don't really apply to it. When I do this multiplication, I get 3.56 grams. Okay, so 0.0387 moles of N2O4 is equivalent to 3.56 grams of N2O4. Or in scientific notation, 3.56 times 10 to the 0, because I don't actually have to move the decimal point at all here. Okay, another example. Okay, in this case, we're going to be working with number of atoms or number of particles, or in this case, the particles are formula units, okay, because this is an ionic compound. We have aluminum chloride, or aluminium, as most of the world would say. And we know that we have 6.17 moles of this substance. So that's my starting point. Okay, so again, I'm standing on the middle of the bridge, but this time instead of going to mass, I want to go to number of particles. So I need one of the conversion factors with Avogadro's number. So in 1 mole of something, in this case 1 mole of aluminum chloride, there are 6.022 times 10 to the 23rd formula units in this case, okay, whatever the particular particle happens to be, of aluminum chloride. These will cancel. I'm left with formula units, which is what I want. When I perform this multiplication, I end with 3.72 times 10 to the 24th aluminum chloride units, okay, or formula units. Again, I have 3 significant figures in my answer because I have 3 significant figures coming from my initial measurement. Again, this is just a definition. Significant figures don't apply to this. Okay, now let's take a little bit of a twist on this. The book doesn't really explain how to do these slightly more complicated questions that I have at the bottom of the page here, but some of the homework will ask you to do this. Okay, and it's not too hard to figure out, but I'm going to show you how to do it in terms of conversion factors, just like the previous problems. So what if the problem asked me, instead of how many formula units of aluminum chloride I have, what if it asked me how many atoms of chlorine there are in 6.17 moles of aluminum chloride? Well, if I continue this, so I'm actually going to need a third conversion factor, or a second, to get a third step. If I think about aluminum chloride, how many chlorine atoms are in each formula unit? Well, there are 3 for each formula unit. So that actually gives me my conversion factor that I need. There are 3 atoms of chlorine in 1 formula unit of AlCl3. Okay, so here I finished with formula units as my unit at the end of the conversion. If I want atoms of chlorine, I need to cancel those units and end up with this unit that I'm looking for here, atoms of chlorine. So if I continued this conversion with just one more step, I could solve this problem. So if I have 1 formula unit, getting sloppy here, there are 3 atoms of chlorine in it. So in this many moles, there are so many formula units, and if I do one more conversion, then I can find out how many atoms of chlorine there are in that many formula units. So we cancel those. We multiply this result that we got here by 3, and that gives us 1.11 times 10 to the 25th chlorine atoms. Okay, that is exactly 3 times this solution that we got for the previous problem. The conversion factor atoms of chlorine, and between atoms of chlorine and formula units, this is also a definition, okay? Or this is just a counting, in fact. We're just counting the number of chlorine atoms in each formula unit. So this, again, significant digits do not apply to this. They do not apply to this conversion factor. They're only coming from the initial quote-unquote measurement that we began with. All right, now here's the ultimate wrinkle. What if it asked me to find the mass of those chlorine atoms that are in this many moles of aluminum chloride. What would I do in that case? Well, if you think about the bridge for a second, what we've done is we started here with moles of aluminum chloride. We converted to formula units, and we converted formula units to a number of atoms. So we stayed on this side of the bridge for that part of the conversion. And then we're being asked for mass, which is over here. So we're going to need to take those chlorine atoms and do a conversion from there, 2 steps across the bridge to get back to mass. So the initial part of this, given 6.17 moles of aluminum chloride, would all be the same. I would set up the initial part of the problem just like this. Converting to formula units. And then to atoms of chlorine. And then I'm running out of space here, but I'm going to continue this conversion down here. Okay, from there now I'm going from atoms of chlorine, which is a number of particles, back to moles and then to grams. So I need 2 more conversion factors. And in 6.022 times 10 to the 23rd atoms of chlorine, that gives me 1 mole of chlorine. And then the molar mass for chlorine, 1 mole of chlorine, there are 35.45 grams of chlorine. Again, we get this from the periodic table, from the atomic mass. Okay, these units all will cancel. And I have converted from 6.17 moles of this compound to how much of that compound is chlorine in terms of the total mass. So I end with a certain number of grams of chlorine, and after doing the multiplications and the divisions all the way across here, I'm going to get, oh, it looks like I didn't actually write this number down. I'll have to use my calculator real quick. Okay, after calculating, it turns out to be 6.56 times 10 to the second grams of chlorine, okay, or 656 grams of chlorine in that many moles of aluminum chloride. Now, you'll notice here there is a quicker way to do this, okay, if you're clever. I don't like to teach it that way because I think that can confuse people and you may not always be able to see this so easily. But this conversion factor here and this one are just kind of the inverse of each other. It's just the type of chemical that they're describing is different. In this case, it's aluminum chloride. In this case, it's chlorine. But the numbers, 6.022 times 10 to the 23rd in the numerator and 6.022 times 10 to the 23rd in the denominator, are actually going to cancel each other out. So you can simplify this conversion. If you see that and if you recognize that, you can sort of bypass this whole step. But I don't like to teach that because students will tend to then start to try to take shortcuts and overlook things which are sometimes important to keep. Okay, so that's a little introduction to the idea of how we can use moles to convert between number of particles and mass and vice versa. We will work some more complicated examples in the next video. If you didn't understand some of this, then get in touch with me through text or email, and I'll be happy to try to help you understand whatever you might be missing.